handouts here. Okay, so let me, since you don't have very many questions, any questions from anything that we did yesterday? Like the lecture, any questions from the lecture at all? Okay, so what I'm going to do is first of all go over very quickly what we did yesterday on trigonometry, okay? So first of all, remember a straight line means a straight line extends to infinity in both directions, right? A ray starts at a point and extends to infinity in one direction only. And what is an angle? Well, an angle is formed when two rays have the same tail. And one of the rays, when you have an angle, one of the rays or one of the sides will be called the initial side. The other one will be called the terminal side. The way we are going to view this is that the terminal side, in order to form an angle, the terminal side starts from the initial side, and then you rotate it until you get your desired angle. If you rotate counterclockwise, you get a positive angle. If you rotate clockwise, you get a negative angle. So this is a positive angle on the left side, the negative angle on the right side. And we talked about the degree measure, but I'm not going to go over that again. Remember acute angles. An acute angle is an angle between 0 and 90 degrees. Obtuse angle is an angle between 90 and 180. Pythagorean theorem, remember that's the if I have a right triangle, and the sides are ABC, C is the length of the hypotenuse, then C squared is A squared plus B squared. Trigonometric functions at acute angles. So if I have a right triangle, and let's say theta is the angle as labeled, and so what's the opposite side of theta? Whatever the opposite of theta is, I'm going to denote the adjacent of theta by ADJ, and then HYP is the hypotenuse. And then what's the definition of sine theta? Well, sine theta is the opposite over hypotenuse. Cosine theta is adjacent over the hypotenuse. Tangent is opposite over adjacent. And then what are the other ones? Well, cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of cotangent. Tangent. So that's what we have here. So that was our definition for the trig functions at acute angles. Now, after that, we found some special values of this trig functions. So we found the values of the trig functions at angles 30, 45, and 60 degrees, right? So in order to find the values of the trig functions at 45 degrees, so what did we do? Well, we said, let's pick a right triangle, which is a 45, 45, 90 degrees right triangle. And then we know that the two legs of the right triangle must be the same, so x and x. And then if the two of the sides are x and x, then the hypotenuse can be computed by using the Pythagorean theorem, right? And that's what we did. We said, well, the hypotenuse would be the root of x squared plus x squared, right? Which is root 2x. So that's how we got the root 2x there. And then we can easily answer, hey, what is sine of 45? Well, sine of 45 would be what? X over root x. Cosine of 45 would be x over root x, right? Sorry, x over root 2x, right? So that's how we are getting 1 over root 2, right? Okay. In order to find out the values of the trig functions at at 30 degrees and 60 degrees. This is what we did. We said, well, let's start with a 60-60-60 triangle. So that's what I have in the third triangle here. That's a 60-60-60 triangle. And then what we did, from one of the vertices, we drew a vertical line to the opposite side. And so that divided the angle into two halves. So then I got the 30 degree here, 30 degrees and 60 degrees, one of the halves would be then 30 degrees. Let me use a pen here. So this angle here would be at 30 degrees now. And this would be a 90 degrees here. And since you have a 60-60-60 triangle, all the sides are the same, right? It's an equilateral triangle, right? Equilateral triangle. And so I am letting each side to have length 2x. And you might say, how can you use 2? Well, so let's say the length is 3, right? Length of each side, let's say, is 3. Well, then I can write 3 as 2 times 3 half. So x would be 3 half. Am I making sense? So I can denote the length of each side by 2x. If I want, I can denote the length of each side by 3x, 4x, 5x. It doesn't matter because we can choose x accordingly, okay? So I am denoting the length of each side by 2x because of the following. So once I have that, then I can say, now look at the right triangle here, which would be a 30, 60, 90 now, right? So that's what I drew here. So this triangle that I drew here, that's basically the same as this triangle here, right? And then the hypotenuse is 2x, the one side is x, then what's the length of the other side? Well, we can again use Pythagoras theorem, right? So if I call this side to be a, right? Then a squared plus x squared is 2x squared. And then from there I can solve for a. And we obtained a to be root 3x, right? So once I got that, then I can answer the following. Hey, what's the sine of 30? Well, sine of 30 would be x over 2x. What is cosine of 30? Well, cosine of 30 would be root 3x divided by 2x, which would be root 3 over 2. Is everybody okay with that? So that's how we are getting those values. Sometimes, so if remember we completed this table and I asked you to complete the last row. If you just, trying to memorize the table by itself, those values sometimes it's hard, right? So, but if you remember these triangles, right? If you remember the first two triangles, right? Then you don't have to remember the table. You can just use those triangles to find out the values, right? Am I making sense? Okay. And then we said we wrote down two identities. One is sine of 90 minus theta is the same as cosine theta. Cosine of 90 minus theta is the same as sine theta. And I gave you a reasoning here that I'm not going to go over anymore. Then we looked at the radian measure. So what's the radian measure of an angle? We said, well, let's start with a circle of radius r. And let's say I have a central angle theta, which is subtended by the arc length c. Okay? And then the radian measure of theta is given by c over r. Okay? So it's the ratio of two lengths. It's the ratio of two lengths. And so the question is, why do we use radians once again? Well, first of all, just remember that in calculus, we use radians, we don't use degrees. One of the reasons is that, think about, if you try to sketch the graph of the sine function, for example, right? If you try to sketch the graph of sine function, you're going to pick the theta values on the horizontal axis, right? You're going to draw the graph of sine theta, let's say. So theta would be on the horizontal axis, right? And sine theta values would be on the vertical axis, right? Am I making sense? So when you sketch the graph of sine theta, then you have to pick a scale, right? Now notice that because sine theta is what? Sine theta is defined to be the ratio of opposite over hypotenuse, right? It's a ratio of two lengths. Radian measure is also a ratio of two lengths. So when you sketch the graph, you can pick the same scale for the vertical axis and the horizontal axis. But if you use a degree measure, can you do that anymore? You can't. Okay. So that's why it is advantageous to use radian measure. Another reason is that pretty soon we will be talking about the derivative of trig functions. Okay. And if we use radian, if you use a degree measure, then those derivative formulas, they don't come out nice. Okay, so basically what I'm saying is we will see later that it doesn't matter what it means, what is the meaning of derivative yet. Okay, if you don't know what is a derivative, just don't worry about it. I'm just telling you there is a formula which looks like the following. It looks like that the derivative of sine x is cosine x. Now, this formula works because you're using radian measure, but if you use degree measure for x, the angle, then you have to multiply this with something. So which formula is nicer? Of course, without the star, right? So so that's why we use this radian measure. Okay, so we'll talk about derivatives and stuff later. All right, so now let's so length of the length of the circumference of a circle of radius r is given by 2 pi r, and then so the 90 degree would be subtended by 1/4 of the circumference, right? So what is 1/4 of the circumference? The 1/4 of the circumference is half of pi r, right? And so the 90 degree angle is subtended by half pi r arc length, right? And so what's the radian measure of 90 degree angle then? Or radian measure of a right triangle? Well, you divide the arc length by radius, right? If you divide the arc length by radius, what do you get? Whoops. You get pi over 2. Right, so pi over 2 is a right triangle. Pi over 2 is the radian measure of the right triangle. How about 180 degrees? Well, 180 degrees is clearly 180 degrees. So 180 degree angle is subtended by half the circumference, right? So half the circumference divided by the radius is what? 2 pi. Sorry, pi. Okay, so you get pi radians. So 180 degrees is pi radians. So usually we use that as our conversion formula between the two measures. And for example, 270 degrees, right? In order to convert that to radians, you simply multiply 270 with pi divided by 180, and you get the radian measure. And in order to convert radian measure to degree measure, you do the opposite. You multiply by 180 over pi, and that's going to give you the degree measure. Okay. Everybody is okay with that? Any questions on anything that we did so far? Everybody's cool with that? All right. So now, what I want to do is, so far we defined sine theta, cosine theta for what type of angles? Because we use the right triangle only, right? We can only define it for acute angles, right? Angles between 0 and 90. But how about other angles, right? So remember again, angle, if you have angles, we define angles like this, right? So on my terminal side, so this is my terminal side. I can, let's say this is my terminal side. So this is the initial side, the terminal side. You see the angle is not necessarily this, right? Maybe I got to the terminal side by going in this direction. That's another possibility, right? But there are infinitely many other possibilities. For example, I can revolve like this and come back here. That's also an angle whose measure is bigger than 360 degrees, right? Because you made one complete revolution. So every time you make one complete revolution, you are going over 360 degrees, right? So this angle is much bigger. For example, let's say I have this and this. Again, this is the initial side, this is the terminal side, and this angle here, I can say that I go like this and come back here. So how many degrees is that? Or how many radians is that? It would be 2 pi is 360 degrees, right? And then plus pi over 2, right? So this angle is 2 pi and plus pi over 2, which is what? 5 pi over 2. But another thing I could have done is that I could also go in the clockwise direction, right? If I go clockwise direction, let's say like this, So one complete revolution clockwise, and then I go what? I add pi over 2. Is that making sense? One complete, so it is what? Negative 2 pi? Negative 2 pi would be one complete revolution clockwise, and then when you add pi over 2, you go counterclockwise because you're adding pi over 2. So what I'm saying is that the green angle is negative 2 pi plus pi over 2, right? You guys agree with that? Or in other words, it's negative 3 pi over 2, right?
If it was pointing down, it would be pi over 2.
So okay, so what I'm saying is that I am what I'm saying is that I am going
one rotation and then 3/4 of another.
What I drew is I didn't mean to. What I was trying to mean is that I go like this and come back. So that's okay. So what I have here is I go one complete revolution and then I go back. You're right. The way I drew it, what I should be saying is I made one complete. Let's see. I started here. Came here, I made one complete revolution and then I went 3 pi over 2, right? Yeah. So let me delete that here and make sure I have a cleaner version here. Okay, let me delete the whole thing. So what I meant to write okay, so this is what I meant to write. I start like this. That's negative 2 pi, and then I go back, right, by pi over 2. So that's going to be what? 3 pi over 2. Everybody is okay with that? Okay, so my point is there are angles which are not just between 0 and 90 degrees, and it is, you might say, do we even need to talk about angles beyond 0 and 360 degrees because you make one complete revolution anyway? And the answer is yes, it is advantageous to talk about angles beyond 360 degrees. So here's here is the definition of the trig functions for angles which are not acute angles. Okay, so anyone remembers the definition of the trig functions using the circle, the wrapping function? So let's see what I mean. Let's say I have a circle centered at the origin. So let me make a circle. Oops. So let's take a circle. And let's say the circle is centered at the origin. Okay, so this is the origin. Okay, this is O for origin. Let's say that the radius of this circle is R. So this is the radius. Let me call this the x-axis, y-axis. The radius of the circle, let's say, is R. And let's say I have an angle. And let's say I have this angle. And the angle is the angle theta. Okay? So let's say the angle theta is basically this angle here, even though it may not be this, because what I'm saying is that, you know, if you have an angle, the initial side is always the x-axis, okay? The initial side is always the x-axis. So the terminal side, I'm saying whatever the angle theta is, the terminal side is what I have, okay? Now, it doesn't have to be necessarily the angle that I drew. It could be I make couple of complete revolutions and then I come back there, right? So whatever the angle theta is, the terminal position is where I drew it. Let's say. Then what I'm going to do is I am going to draw a vertical line from this point here onto the x-axis. So again, what I'm saying is that the terminal side of your angle theta intersects the circle at a point, and from that point I am making a vertical line onto the x-axis, right? Okay, so that point, let's say, is P. This point, let's say, is P. And now I got a right triangle, right? You guys realize that I have a right triangle? That right triangle will be called the reference triangle. Okay, so I'm going to use the word reference triangle, which is basically this triangle, and then the angle here, the angle that I have here, I am going to call that the reference angle. Okay, so the green angle here is the reference angle. Everybody is clear on that? Okay, and let's assume that the point P, what are the coordinates? Let's say the coordinates are given by x comma y. So can someone tell me what's the length of the adjacent of the green angle? What's the length of the adjacent of the green angle? X. So x would be this length, and then what's the length of the opposite of the green angle? It's given by y. Very good. So this is y. And what's the hypotenuse here? What's the length of the hypotenuse? Yeah, but what is that? This is a circle of radius what? It's a circle of radius r. So is that the hypotenuse is always the radius, right? So this side is r. Okay, so we are going to say then, we are going to define cosine theta as usual to be the adjacent over the hypotenuse. So this would be x over r, and then sine theta is y divided by r. Everybody's okay? We're going to define sine theta. Remember, theta is not the same angle as the reference angle, right? But the green angle is the reference angle for theta. And we are defining cosine theta and sine theta by using this right triangle. Now you might say, what is the difference between this and before? Well, notice that x could be negative now, right? X could be negative. And same way for other angles, y could be negative, okay? So that's the difference. Now, again, what is the summary here? Well, you have a circle of radius r. Whatever angle you want, that angle theta will have a terminal side. The terminal side intersects the circle at a point. Okay, that point has coordinates x and y. When you divide the first coordinate by r, you get the cosine theta. When you divide the second coordinate by r, you get the sine theta. Am I making sense? Everybody's clear on that? Okay. Now you might say, wait a minute, you have a circle of radius r, and you're defining sine theta and cosine, which is all cool, but it seems like the definition depends on radius. Would that happen that if I use a different radius, then the values will be different? Then I have a really bad definition, right? The way I define cosine theta and sine theta, right? What if I change the radius, right? Would I get different values for the same angle? Am I making sense? So suppose that I make a bigger circle here, and I still have the same angle theta. Will these values change? The values, you see, if they were different, then I have a really bad definition, and we can forget about trigonometry, right?
They wouldn't change because the scale is so the same.
See, they wouldn't change. Let's see why. Let me try to give you a reasoning why these values would not change, even if I have a different radius. Okay, so I want to make a comment here, which is cosine theta, sine theta. They are independent of the radius r. Okay, so the values of this trig functions, they don't depend on r, even though we used r to define these functions. So let's see why. Let's say I have a circle. I need two circles here. Let's see if I can make them. Say it again. Yeah. This line. Yeah. So cosine theta and sine theta, the definitions of these two functions are independent of r. Okay. Again, you guys realize that if it is not independent of r, then we are screwed, right? The definition just doesn't work. Okay, the definition wouldn't work. So here's the reasoning. Here's the reasoning. Let's say I have let me make two circles here, a smaller one and a bigger one. That's a better one. Let me delete that one. Okay. Was that right line right here? Right here? Go left? Oh, okay, maybe I can move that. Okay, good enough? All right. So here's my x-axis, let's say. Here's my x-axis, and let's say here's my y-axis. Okay, so let's say the radius of the let's say the radius of the inner circle is R1 and the radius of the outer circle is R2. Okay, so let's make a angle again. Then my angle is let's say theta. And so in order to, so for the inner circle, right, what would be the value of cosine theta and sine theta? Let's see. So we are going to make a vertical line from the intersection of the terminal side with the circle to the x-axis, right? So I need another one from here. Okay, I have bad scaling, but I'm going to draw it this way, okay? So let's say I have these 2 points. One of them I'm going to call P1. The other one would be called P2. Let's say P2 has coordinates x2, y2. And P1 has coordinates x1, y1, okay? Everybody is clear? Then what is cosine theta? What is cosine theta? Cosine theta for the inner circle. For the inner circle, the cosine theta would be what? X1 over R1, right? Yeah. And sine theta would be? Y1 over R1, right? For the outer circle, cosine theta would be x2 over r2 and sine theta would be y2 over r2. Now, why are these the same? So why is it that x1 over r1 should be this? Why is it that x1 over r1 is the same as x2 over r2? Anybody? Yeah.
Because theta is the same.
Yeah, but I'm saying why do you think that they are the same? I mean, that's what I want to show. If theta is the same angle, then this, no matter what radius I use, the values of sine and cosine would not change. Yeah.
Because the triangle is the same.
The triangles that I have here, right? They are similar triangles, right? You guys realize that? They are similar angles, they have the same angle. So when you have similar angles, the ratio of corresponding sides are the same, right? So that's why these two are the same, these two are the same, okay? So now we know that these two are the same and these two are the same because the triangles here, they are similar by using similar triangles. Everybody's okay? Well, since it doesn't matter what radius you pick, well, let's just use radius 1, okay? So we often use radius 1 because it doesn't matter which radius I pick. So let's make a unit circle. Let's say this is the x-axis, this is the y-axis, and so this is let's say the radius is 1. So this point has coordinates 1, 0. This is still the origin. This is a circle of radius 1 centered at the origin. And let's say if I have an angle theta, okay, if I have an angle theta, let's say the terminal side intersects the circle at P, and P has coordinates x and y, okay, then I can make this the reference triangle again, and and then what is cosine theta now? And what is sine theta? x over 1, right? So this is exactly just x, this is exactly just y, right? Because the radius is 1. Well, you divide by radius, but the radius is 1. So if I have a unit circle, so this is called a unit circle. This is the circle of radius 1 centered at the origin, unit circle. So if I use a unit circle, then what are the values of cosine theta and sine theta? Can someone give me a description of the values of cosine and sine? Well, they are just coordinates of points on the unit circle, right? See, cosine theta is the first coordinate of P. Sine theta is the second coordinate of P, right? So the cosine theta and sine theta is a point on the unit circle, right? So I can say this point here, P, the point P has coordinates what? This is the angle theta, right? The point P has coordinates cosine theta and sine theta, right? So if I have a unit circle, whatever the angle theta is, it intersects, the terminal side intersects the circle at a point P, then the coordinates of the point P are given by cosine theta and sine theta, right? You guys realize that? So what I'm saying is that I have a unit circle, circle of radius 1, centered at the origin. That's the unit circle. I have an angle theta. Whatever the angle theta is, the terminal side intersects the circle at a point P. And what I'm saying is that the coordinates of P are given by cosine theta and sine theta. Because cosine theta is x, sine theta is y, right? Yeah. What wouldn't change? Measures of the triangles. What do you mean by measures of the triangles? Yeah, but you see, you're going to divide. So what is sine of theta? Sine of theta would be the opposite over the hypotenuse, but the hypotenuse is always 1 here, right? So the opposite is always the x coordinate of the point P. I mean, think about any other angle, right? Any other angle would mean that P will be in a different place on the circle, right? So the x coordinate is always the length of the adjacent, right? And the second coordinate is always the length of the opposite. You realize that? And you're dividing them always by 1. So that's why the first coordinate is cosine theta, the second coordinate is the sine theta. Everybody realizes that. The first coordinate, so if you have a unit circle, okay, and if you pick a point P on the unit circle, and let's say from the point P to the origin you make an angle, then the first coordinate of the point P is given by cosine theta, second coordinate of the point P is given by sine theta. Am I making sense? Any other questions? Okay, so we can right away find some special values, right? So what are they? Notice that this point has coordinates 1 and 0, right? What are the coordinates of this point? 0, 1. What are the coordinates of here? Negative 1, 0. This point here. Okay. So from this, what can we say? So keep that picture. Okay. And let's answer a couple of questions here. Let's say I have the value of theta to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then let's say I have, I want to know what are the values of cosine theta and sine theta. What's the value of cosine 0? 1. Sine 0? 0. Because again, the first coordinate gives you cosine, the second coordinate gives you sine, right? because it's a unit circle. And cosine of pi over 2 is what? Cosine of pi over 2? 0, because, and then this would be 1, right? What is cosine of pi? Negative 1 and 0. What is cosine of 3 pi over 2? 0 and sine? Okay. And this would be 1 and 0 again, right? Everybody's okay? So right away we know those values. Okay. Coterminal angles. Anyone knows what that means? Two angles having the same. Remember, right now we are fixing the initial side to be always. For any angle, the initial side is always the same as the x-axis. Okay. So then, two angles are called coterminal if they have the same terminal side. Okay. Same two angles having the same terminal sides. For example, let's make a circle first. Yeah, I'll go in a bit. Okay, let's say I have the angle right here. Okay, I'm going to call that angle alpha, which is this angle here. Okay, and this angle and the green angle, which is this angle, beta, they are coterminal, right? They are coterminal because they have the same terminal side. Am I making sense? So coterminal means so alpha beta here are coterminal. There are many other possibilities for coterminal angles, right? For example, instead of picking, let me draw another one. Oops. Well, I'm going to work with this. Okay, so let's say I have again the angle right here. Let's say that angle is alpha right here. And then if I make, let's see that if I make another angle which is going this way and coming like this, right? I'm going to call that beta. Okay, whatever that angle is, however many times I revolve, doesn't matter. My point is, alpha beta, they have the same terminal side. Okay, so here again, alpha beta have same T. Okay, I'm just going to say T for terminal side. Now, can someone tell me that suppose I have alpha and beta, they are two terminal sides. They are two, alpha, beta are coterminal angles. In that case, can I say cosine alpha and cosine alpha and cosine beta are the same? Is my question clear? Alpha, beta are coterminal. If alpha, beta are coterminal, right? Coterminal, then cosine alpha is the same as cosine beta, and sine alpha is the same as sine beta, right? You guys agree with that? Because if I have, remember, what's the definition of sine and cosine? Well, if I have a unit circle, then the coordinates of the point P gives you the cosine value and the sine value, right? What is the point P? The point P is the intersection of the terminal side with the circle, right? So the coordinates of P determines the values. So if alpha and beta, they have the same terminal side, then the P is the same, right? So the same x and y again, and then the values are the same, right? Am I making sense? If alpha, beta, they are coterminal angles, then cosine alpha and cosine beta are the same, sine alpha and sine beta are the same.
Okay, the cosine is with the sine.
Yeah.
The one we change.
No, for example, here's what I'm saying. You see, here alpha and beta are coterminal, right? In my picture. So notice that if I make a right triangle from this point, right? This is the point P here, right? So let's say the coordinates of P are x and y. So for alpha, what is sine alpha? Let's say this is a unit circle.
Sine is y over 1.
Yeah, so sine alpha is y over 1. What is sine of beta?
Where is the y and s compared?
Well, for beta, y is the same still, right? Whatever the angle is, remember the definition is whatever the angle is, the terminal side intersects at a point P, right? And from the point P, you make a vertical line to the x-axis, right? So it doesn't matter how you got beta. What is beta? As long as beta has the same terminal side, you're getting the same point P. Is that making sense? See, no matter what beta is, you're coming back to the point P. From that point P, intersection of the terminal side and the circle, that's the point P. From there you make a vertical line to the x-axis, right? That's how you get the opposite and the adjacent, right? Am I making sense? So again, the second coordinate of the point P tells you the sine value. The first coordinate tells you the cosine value. Right? Okay, this is what you want to remember, okay? Unit circle. Whatever the angle is, the terminal side intersects the circle at a point P. That point P has two coordinates, x and y. X is the cosine theta, y is the sine theta. Okay? So what I'm saying, the cosine and sine values, they depend on the location of the terminal side, right? It doesn't matter what is the measure of alpha and beta. What it matters is that what is the position of the terminal side, right? If alpha, beta, they have the same terminal side, the cosine values for them are the same. Okay? Cosine values are the same. So here's a specific case of that. Let's look at a specific case. Let me make my circle again. Okay, let's say I have an angle theta again. So let's call that theta. Let's say theta is this angle here. Do you realize that if I add 2 pi and then come back here, so what is that angle? That angle is 2 pi plus theta, right? So notice that 2 pi plus theta and theta, they have the same terminal side, right? Let's say that this point is P, and what if I have negative, what if I have, well, I'm going to see that later. So can I say then cosine of theta plus 2 pi is the same as cosine theta, right? Because they have the same terminal sides. Same way, sine of theta plus 2 pi would be sine theta, right? You guys realize that? Because if I add 2 pi, I'm coming back to the same terminal side, right? Now, what if I subtract 2 pi? Theta minus 2 pi. What's the terminal side for theta minus 2 pi? The what? Actually the same as the terminal side for theta, right? Because, okay, what is theta minus 2 pi? Minus 2 pi means you're going to go clockwise one complete revolution, right? So negative 2 pi means you're going to go this way. And then when you add theta, you go back to theta in the counterclockwise direction, right? So if I have negative 2 pi here, I still get cosine theta, right? So cosine theta plus or minus 2 pi is always going to give you the same thing as cosine theta. This is why we say that cosine and sine, they are periodic with period 2 pi. Okay, sine function and the cosine function, they are periodic with period 2 pi. Okay. What I mean is that if you know the value of cosine theta, right, and then if you add or subtract 2 pi, you get cosine theta again, right? Same as cosine theta. So this is why it's called period 2 pi. When I draw the graph of this function, you'll see what it means to have period 2 pi in terms of the graph. Okay. All right. Any questions on this? Can somebody tell me what happens when instead of 2 pi I add 4 pi or subtract 4 pi? Same thing, right? 6 pi? But what if 3 pi? No, it's not going to happen, because if you add just pi, right, you don't get they are not coterminal anymore. You realize that theta and theta plus pi, they are not coterminal, right? You realize that? Okay. Well, for example, let me just give you one quick example here. What is theta plus pi? What is theta plus pi? What's the terminal side for theta plus pi? Is this one, right? Theta plus pi. You realize that? So theta plus pi is which angle? Theta plus pi is this angle here. Okay? So you realize that one thing you want to realize here, if the point P has coordinate x and y, let's call this point here Q. Okay, what are the coordinates of Q? Anyone knows? Negative x and negative y. If for theta you got P, right? If P has coordinates x and y, then when you add theta plus pi, the point Q will have the same coordinates with opposite signs. Okay, is that making sense? So what is cosine theta and sine? What's the relationship between what is cosine of theta plus pi and what is cosine of theta minus pi? What are those? Oh, sorry, this is plus. What is cosine of why did I write cosine twice? Sorry. I want to write sine here. So sine of theta plus pi. What is cosine of theta plus pi? Yeah.
Equals negative cosine theta.
Negative cosine theta, right. Because what is cosine theta? Cosine theta is x. Cosine of theta plus pi would be negative x. Right? Sine of theta plus pi would be y. Sine of theta would be y. Sine of theta plus y would be negative y, right? So then sine of theta plus pi is negative sine theta, right? You realize that? Everybody is okay? Now, you see, I have four identities here, right? They work no matter what theta is. In general, theta doesn't have to be an angle in the between 0 and 90. Theta could be anything at all. This identities still hold. Okay. All right.